Previously, I trained an XGBoost regression model to predict the exact stock price. It didn't turn out too well. The predicted prices are way off the actual prices. This time around, I'm doing it differently. I will simply train an XGBoost classifier model to predict if the stock price will close up or close down the next day and assess its performance based on a few key metrics. Based on the model prediction, I will then either open a credit put spread for the stock index if the model predicts that the price will close up, or open a credit call spread if the model predicts the price will close down. If the credit spread closes out of the money, I get to pocket the premiums earned. If the credit spread closes in the money, I will incur losses. Does the model do well enough to make money? Let's find out. This time round for feature engineering, I am going to use the Python library pandas-ta. It is a Python library which contains technical trading indicators. I am going to include some of the trading indicators from the library. Also, the financial markets are very interconnected. Thus, I will include other tickers which are closely related to the ticker that I will be predicting and see if there are any predictive powers there. I will package them all in a function that will preprocess the data and include a code that will split the data into training and test data, with the final row of data for prediction. Lastly, I will apply a standard scaler on the data to normalize it. After we have completed the feature engineering and built the data pipeline, we can run the function which we just built. I will input some necessary inputs into the function, such as the ticker to trade on, which in this case is the SPX index, the start date, training data from 2020, and the test start date period from the start of this year 2026, and the current date, which is the cut-off date for the training data. It will output different data frames, which we will use later in training the model and assessing model performance. We can inspect the data frame and see that it is in the expected format of features being in the columns. One thing to note is this time, I have performed a standard scaler on the variables, so they are all standardized to a scale. This time, I have also increased the number of features to approximately 250 features. Hopefully, this will be helpful in prediction. We can also print out the value count of the training dataset, and we can see that there is a slight class imbalance, where there are 820 days where the stock index price closes up compared to 688 days of stock index price closing down. The slight class imbalance is still acceptable, and so I won't be using any balancing dataset techniques. Before I trained the model, I was curious to see if there are any features which have a strong correlation with stock price prediction. Hence, I computed the correlation of the features and the target variable, and plotted a correlation matrix of the top 10 correlated features. And we can see that there is no strong single feature that has a strong correlation with the closing stock price movement. We can refer to either the first row or first column to compare the correlation between the features and the target variable, and the highest absolute coefficient is 0.06, which is not much. Looking at some of the features, there appears to be some correlation between the features. But as I'm running XGBoost, it will auto-select the features to be used, and I'm not too concerned about correlated features. Furthermore, this only refers to linear correlation, but they could be correlated in non-linear ways, and I would like to capture that relationship as well. Now, let's train the model using the default model parameters to predict the training data and assess the model performance on a few metrics. We can print out the accuracy, precision, recall, confusion matrix, and the classification report. Before going into the metrics, we can see the training data label counts, and it's fairly even and not too imbalanced between closing up and closing down. Next, we can inspect the model performance. As we are concerned with how accurate the model is at predicting stock closing up or down, which is both ways, the metric we are primarily interested in is accuracy. We can also assess the precision if we are interested in only predicting stock closing up as well. The accuracy and precision metric are approximately 60%, meaning to say on average, the model predicted the correct stock closing direction 6 out of 10 times. Referring to the confusion matrix and classification report, we can see that the model is slightly better at predicting stock price closing up. We can also plot the ROC curve to see how well the model distinguishes between price closing up and down. Unfortunately, looking at the area under the curve score of 0.56, it is only performing slightly better compared to a random coin flip in terms of predicting the results. Let's count the number of correct predictions based on training data. We can see that it got 70 predictions correct while 48 predictions wrong. This is in line with the accuracy and precision scores of approximately 60%. Next, let's plot a histogram plot of binned predicted probabilities. Based on the histogram plot, it does seem to agree that the model is not very good at predicting the direction. Even at greater than 70% predicted probability, there is still a high proportion of incorrectly predicted directions, denoted by the blue bars. The model predicts only slightly better than a coin. But wait, 60% accuracy and precision are still better than 50%. Is the model able to make money? Let's find out by creating a table and computing the win and loss rate at bins of 10% predicted probabilities from 0% to 100%. However, to compute the amount earned, we need to first understand the asymmetrical risk-reward ratio of credit spreads. Here, we have an actual risk-reward profile of an SPX index credit spread for June 23. For a short put spread, the upside is about $80 while the downside is capped at -$400. This means the reward-to-risk ratio is 1 to 5. As such, to be conservative, I will compute the estimated earnings for gained credit spreads to be $50 and credit spread losses to be $400. From the table, we can see that the win rate is hovering around 60%, with the best win rate at the 0.8 and 0.2 thresholds, which isn't surprising as they just flip sides. Unfortunately for the earnings, we can see the poor reward-to-risk ratio is directly impacting the earnings, where we would make a loss regardless of predicted probability thresholds at the current level of reward-to-risk ratio. What if we increase the profit that we make on trades that we win? Will we eventually be able to make money? To that end, we can create another table and perform sensitivity analysis by increasing the profit earned at an increment of $10 all the way to $100 credit spread. Unfortunately, based on the table results, with the current model performance, we will still lose money on all levels. We can also plot line plots to see the estimated cumulative earnings based on a credit spread profit of $50. I will plot two line plots. The first is based on the default predicted threshold of the model at 50%, and the second is based on the predicted threshold at 90%. As expected, we see losses for both thresholds, with the default threshold of 50% losing the most money, while the losses for the 90% threshold is more controlled. All we have seen is the model not able to make money at its current performance. But do we even know what is the minimum win rate to break even? To do that, we can build a simple function to calculate it using two inputs, the win payout and the loss. For our case, if we set the win payout to 50 and the loss to 400, which is the same as a reward-to-risk ratio of 1:8, at a minimum, we need to win 89% of the prediction with the model to break even. In other words, the model has to predict 9 out of 10 times correctly to break even. The odds are quite bad and stacked against my favor. Using the same function to compute the minimum win rate or break-even point required if the reward-to-risk ratio is 1:8 at a credit spread profit of $50. We can extend it to various credit spread profits and compute a table for sensitivity analysis. Referring to the output table, we can see the required win rate at different levels of credit spread profits till $100, and at the reward-to-risk ratio of 1:4, the minimum win rate is 80%. This means the model must predict 80% of the closing price accurately for us to break even. This shows the risk and difficulty in making money trading credit spreads. Despite the model not being able to predict well, can we somehow look at the features that the model thinks is good for prediction? Well, one of the benefits of training an XGBoost model is that it has a feature importance method that allows you to see which features are useful to the model when it makes its prediction. We can call the method and rank it by its absolute value. Sorted by the top importance, we can see that the ratio of the open to lower Bollinger Band of period 20 days and 2 standard deviations apart is the most useful in model prediction, based on the features I have used. We can also use the plot importance function to plot model feature importance. Here, we can see the features ranked by importance score, with the top feature being the ratio of the closing price to the opening price of the dollar index 2 days prior. One thing to note is that the metric used for the feature importance method is different from the plot importance function. Thus, you will notice a difference in the top features listed by the two. You can add an argument of importance type set to gain for the plot importance, and you will get the same features as the feature importance method. For the plot importance, the default importance type is weight or frequency, which measures the number of times a feature is used to split data across all trees. The plot is interesting as it seems to suggest that the ratio of close and open price of the dollar index 2 days prior has some importance to predicting future SPX index price. And it is not alone, as we can see the same for the third feature, which is the ratio of close and open price of the ticker USO 2 days prior ranking quite high as well. We might need to explore this future as these point to them being leading indicators for predicting SPY index prices. Training the model and assessing it is good and all, but how do we see it actualized in reality? Well, we can use the model and do a one-time step ahead unseen data. From the custom function used to prepare the data, I have separated out the last record of data for prediction. We will use it to predict if the stock index closes up or down on the next day. As of the making of this video, the date on the last record is the 24th of June 2026. And we will use it to predict the stock closing on the 25th of June 2026. From the model prediction, we can see that the model predicted that the stock index will close up with a probability of 77%. Did the prediction turn out to be accurate? Not quite. As we can see, the stock index closed down, albeit by a small change of minus 0.01%. Depending on the threshold used, it can be argued that the model has some predictive power. However, this result reveals a potential issue with the model we built so far. Previously, we assumed that the stock index will move only either up or down, a binary outcome. But what if the index closes with a small change from the previous closing, which means to say it closes within a tight range as what is happening here? The model might not be able to predict well as we have only trained it on binary labeled outcomes. Perhaps if we define a third labeled outcome, which is a range bound, the model might be able to predict better. Now that the model is trained, can I use it for actual prediction? Not quite exactly. There are many things which I need to do to adjust it such that the model can actually predict at the expected win rate to make money. To start, I can add additional features to try and improve model performance. Secondly, I can change the labeled data to include a tight ranged bound label and retrain the model. This might impact the model performance. Thirdly, I can calibrate the model's predicted probability. Because XGBoost minimizes a loss function aggressively using gradient boosting, its raw predicted probabilities tend to bunch up away from 0 and 1. An XGBoost output of 0.85 might not actually mean there is an exact 85% real-world empirical frequency of that event happening. Fourthly, as if the model only predicts the direction of the stock closing price, it doesn't tell you exactly which level to place the credit spread and the amount of premium which we should accept. If the ticker gaps up or down and the model predicts accurately, it doesn't help if there isn't a suitable price point with a margin of safety to place the credit spread. An alternative to this might be to trade on predicted by signals of the underlying ticker itself rather than credit spread options. Lastly, this is only one of many other possible models to train, and I can train other models to compare performance and also train and predict other tickers as well. As usual, I have linked the code in the description box for those who are interested in trying it out, but I have left out the code for the model features and trading indicators. Do you have any thoughts on it? Feel free to comment in the comment box down below. If you liked this video and would like to see more content of this nature, please be sure to like and subscribe as well. Thanks for watching, and until next time.